All right, so what do you need to know about heaps? The first thing you need to know is that it has its own invariant, and you should learn it, right? And it's all, what are heaps good for? They're good for priority queues. And what are priority queues wanting to do? They're wanting to find the maximum or find the minimum fast, depending on whether it's a max or a min queue, right? And so where's the max? The max is at the top, is the root. And then you think, where are the others? Well, they're going to be sort of sorted, but not really. And what do we mean by not really? Is what's on the left and what's on the right doesn't matter at all. But as you go down, they have to go smaller, right? So for every node, all of your children are smaller, right? Or equal to, right? Everybody good? That's the one property. The other property is that we don't actually store it with a binary tree with pointers. Why? Because our goal is to be fast here. And if you just do it in an array, it's faster, right? And in order to store an array, they're gonna get stored in this order, right? The root, I'm indexing by 1. Why? Because the math is easier. If Jackie indexes by 0, you have to figure out the math is going to be a little harder, but you figure it out, right? So we put it in 1, 2, 3, 4, 5 up to 9, right? That's how the order they get stored. And because we do that and we want the array full, the tree has to be filled in this order, right? Has to be balanced, and the last row is filled from the left, right? So that's another system invariant that if we tell you to change the tree at all, you better have those two invariants on your new tree, right? You got these invariants, whatever, here, you got to have them here, right? Oh, I erased loop invariant. You got to maintain it, all right? Now, what do you do? What operations do you do on a tree? You do, I'm at a node. Who's my parent? Who are my children? Right? Those are the only operations we do. And if you just eyeball it, you'll see 5's parent is divide by 2, round down, right? And 2's children are you multiply by 2 and you multiply by 2 and add 1, right? Everybody see that? So that's how you get from the parent to the children. And if we index by 0, it would be the same plus or minus 1. There would be some weird changes. Right, everybody good with that? All right. So now, oh, this, I see, this is the review. I was about to say, that's not the slide, because we just did it. But this is a review slide, so things have been deleted, right? So, yeah, what are the things you have to be able to do? Given an array, you think about it as a tree, and you move things around until you get a heap, right? And how do you do it? You recurse on the left, you recurse on the right, right? So this is a heap, and this is a heap, right? And now a common place to be is that the whole thing is a heap, meaning every node has the children smaller, except for one node is a problem, right? And what do we do with that one node? That one node bubbles up or bubbles down. All right, people, let's go through this example here. All right, so what are we going to do with a heap? We're going to use it as a priority queue. We're going to delete the top element, right? So there's 21 is the maximum. And so what do we do with it? We pop it, right? Now, you'll see, right? It was at 1. The maximum's at the root at 1. It's gone, right? But, oops, now 1 is empty. We don't want that. Everybody see that? So then people say, well, why don't we bubble things up to fill it, right? And if you bubble things up, we don't really know where it's going to come from and what shape it's going to have, right? We also need the loop invariant that it has the right shape. In order to have the right shape, who do we have to kill? We have to kill the last guy, right? The 9 has to go, right? So, right, what do we do is we're going to delete the 9. And what do we do with the value that was in 9? Right? 9 was, there was a 3 over there. Why is it 3? Because it's small, right? It's near the bottom. It's a small guy. So what do we do with it? We move it to the root, right? We took the 21 out, and we moved the bottom one to the root. Now we have the right shape, right? Now we have the situation which I talked about. The whole thing is a heap, except for one guy, which is a problem, right? And our one guy who's a problem is the 3, right? So how do we deal with the 3? Well, we compare, right? This is a heap and this is a heap, right? So we call heapify. And how do we do that? He bubbles down, right? We want to say, who goes at the top? The max goes at the top. Where is the max? Well, the max of the left is in 2. The max of the right is in 3. So the overall max is one of those 3, right? And whichever, we see which one's bigger. And the bigger one moves up, right? So here I'm saying the guy in 2 is the biggest. And so the guy in 2 moves up, and the 3 comes down, right? And then, oh, of these 3, we put the biggest. Well, the biggest was in 5. So the 5 comes up, the guy in 5 comes up, and the 3 comes down, right? And now, oh, look it, 3 is pretty happy because it can't go down any further, right? And so we do all of this in log-in time, right? Everybody good? Right? Oh, now we want to insert somebody, right? How do we insert him? Well, if we want to keep the right shape, we put him there, right? Was of length 8, now it's of length 9. And now the 21 has to bubble up, right? To bubble up, we compare it just to its parent. And we swap, right? And then we swap, and then, oh, we're happy where we are, so we stay there. Right? Everybody good? Oh, and then, yeah, then there's all this. If the outside world is talking to you, then you need pointers in and pointers out, right? So hopefully if there's a question like that, you have to just remember pointers in and pointers out and maintain your invariance, right? Heap sort. You know, heap sort is nice. It has this same, you know, like any algorithm, you want to say, what is my invariant, right? And my invariant, if you're doing insertion sort, remember insertion sort, my invariant is some numbers are over here sorted, and the rest are over here not sorted. And what do I do is I take the next number and I insert it, right? Everybody get insertion sort? All right, so here we're going to have the same thing. The numbers here are sorted, and the numbers here, the numbers here are sorted, and the numbers here, well, they're a heap, right? So everybody see that? These are all our numbers. These guys are sorted. These guys are a heap. And then what do? We say, well, what are we going to, oh, no, this isn't insertion sort. This is selection sort, right? we're going to select from the guys we haven't looked at, right? The biggest, right? So of the ones we haven't looked at, who's the biggest? It's a 5, right? So where does 5 go? It goes here, right? So we just take the 5. Oh, we put the 5 and we put it here, right? And then this conveniently gets one bigger. And our heap gets one smaller, all right? But the 5 was here, right? We moved the 5 from here over to here, and and we moved this guy over here, right? So here is where the 5 is. We take this number out, we swap them, right? And now this guy is at the, right? Whoever was here is at the top, and he bubbles down, right? Does that kind of make sense? Or maybe I'm losing you. Right? Well, think about it, and we're running out of time. Okay, we didn't do that. You want to do any questions about those guys? Heaps? Kind of get heaps? Right? All right. So now we want to do things in constant time. All right? And so what we want to do is these keys are going to come from some very large universe of possible keys. And we don't know what keys are going to come in the future, right? And we want to store them in a small array. How big is this array? It's going to be of the size so that it's never more than half full, right? If it ever gets more than half full, you just throw it all away and start over, all right? So, and then what we're going to do is before the adversary knows what the keys are, right? It's how we do the random algorithm. I tell you the algorithm, but I don't flip the coins yet, right? And then the adversary comes up with the keys, right? So the adversary doesn't know the random flips. And then we come up with random coin flips to come up with this hash function, right? People get that? All right, so we have this hash function, and then 5 comes, and we say, where does 5 go? Well, you see 5 goes down here, right? And you see, where does 9 go? Well, 9 goes up to 5, right? So you put it there, right? You just follow the hash function. So people following that? And then how do you search? Well, I see where would 5 be, right? I follow the hash, and there it is, right? Everybody's good. Everybody follow this? All right. So there, right? I do like, I don't know, I can imagine putting this on a test question, because I like 1090. People who taking 1090 from me will have an advantage. But just so you can see here, what are we saying? We're saying I come up with an algorithm. This is my hashing algorithm, such that no matter what input I'm given, I flip the coins, and I'm going to get the right answer, but the running time, the expected running time is going to be small, right? Right? Because the adversary doesn't know the coin flips, right? No matter what, the point here is no matter what input the algorithm gives, right? The adversary gives, right? The adversary is going to come up with really bad, right? The adversary knows the algorithm, but doesn't know the coin flips. So no matter what input the adversary comes up with, when you flip the coins, the expected running time will be small, right? Because the expected number of collisions will be small, right? People get that? I do think that that's worth knowing, right? So I can imagine me putting that question on. All right, you want me to say anything here again, or did you get it? Am I losing you? Yeah, all right. So I'm a believer in you have any math concept that you're trying to understand, you're trying to prove something about it, you write it down in this first order logic method for all exists, all right? And then I like to play a game where you read it from left to right, right? And when it's an exists, the prover has to come up with it, right? And when it's a for all, the adversary comes up with it, all right? So in this game, I tell you the basic idea of, I write the code, right? For heaps or heaps here. Not these aren't heaps, these are hashing. I write the code for hashing. And then the adversary comes up with the input. And what is the input in this case? It's what keys are going to get stored, right? And you might think if the adversary knew my algorithm, he could give me keys that all land all collide in the same cell, right? But the reason the adversary can't do that is because the adversary doesn't know the hash function, right? He knows there will be a hash function, but he doesn't know what it is. So he doesn't know which inputs are going to make, which keys are going to collide. If he doesn't know the hash function, he doesn't know which keys are going to collide, right? So he doesn't know which keys to give you, right? And what we're trying to state is it doesn't matter which keys he gives you, right? He really has no power to hurt you. There's no keys that he's going to give you which are going to be particularly bad. Why? Because once he fixed the input, then we flip the coins, right? When we flip the coins, we get a random hash function, right? And what we can prove, not we collectively, but what the universe has proved, right? You won't have to prove it, right? What you can prove is that if you take a random hash for any hash function we get, the algorithm will work, right? It's not going to go bad. If you have lots of collisions, it might take a long time, right? But it will work, right? So that's one thing. No matter how many collisions there are, it will work. The other thing is if you choose the hash function randomly, then the expected time will be order 1. Right? Does that make sense? And what is the real takeaway here, other than I love first order logic, and that's why I teach it, is that the reason we use randomness is to hide what the algorithm is doing so that the adversary who's coming up with the worst case input doesn't know how to mess you up. Right? Yeah. No, what you're kind of, yeah, so what I hear you saying is I then look at the input, which are the keys, and I find a hash function which will defeat those keys, right? No, we're not allowed to do that, right? That's too, one, it would be too hard, and two, it's against the random game, right? We still want to somehow say, I give you an algorithm and you give me the worst case input, right? So what you're doing is changing the algorithm, right? You're not allowed to do that. So all I'm doing is I'm choosing these R's randomly, right? It's not that I study the input and then look at the input and choose the R, right? In fact, in reality, what happens is I choose the algorithm and I randomly flip the coins and then the input comes, right? And the theory is that if the adversary chose the input without knowing the random coin flips, then it would be fine, right? That it would be unfair for the person coming up with the input to have looked at my random coin flips, right? So you could say I come up with the coin flips first, but they're hidden from the adversary, right? Does that make sense? Yeah. Every key is going to be put somewhere. On the R?
All the random hash functions and like all the possible hash functions, isn't there going to be a combination that with some input and some hash function is actually becomes the worst case?
Yeah. So here there's two ways of dealing with the coin flips, with the for all or versus expected. And what we're going to say here, and the two things we want the right answer, and we want it to be fast, right? And so in this case, I'm going to say, no matter what the coin flips are, it will give you the right answer, right? Right? Because we'll just work harder, right? If there's lots of collisions, we'll just work harder, right? So we will get the right answer. But some coin flips are going to have really bad time. And some coin flips are going to have some coin flips are going to have hash functions for which there's lots of collision, and then the running time will be high, right? Right? So you give me any input, there's a hash function where all those keys get put to the same place, right? And if you get those coin flips, the time is going to be horrendous, right? But the probability that you get that one is small, so the expectation is still good, right? Does that make sense? Yeah. If I had for all on both of them, it would be dumb, but no. Yeah? If this was 1090 or this was 3101, I would expect you to be up on first order logic and be able to write this down, right? But I don't think I'm going to expect that of you, right? So let me tell you what I would like you to remember about this. I'd remember, yeah, it's not a deterministic algorithm, it's a randomized algorithm, right? And why did we make it a randomized algorithm? Well, if it was the deterministic algorithm, and I told you what my deterministic algorithm was, then the worst case input would have keys that all collide in the same box, and we wouldn't be happy, right? And to me, that seems unfair, right? So how do we get around that is you don't let me look at, but on the other hand, if I got to look at your input and then design my algorithm, that would be unfair, right? So how do we compromise between these two? We compromise by, I will tell you my algorithm, but not my coin flips, right? So the reason, what are you trying to remember from this? The reason we do randomized is because the worst case running time for a deterministic algorithm is really bad, right? Why? Because if the adversary knows your algorithm, the worst case input is bad. But if we flip coins, then for any input, right? That's what we're saying. For any input, a random R does pretty well, right? And that's the idea of random algorithms. So have you guys done quicksort yet? Right? What's quicksort? I have a bunch of numbers. I choose a random pivot. I put the pivot here. Then I put everybody smaller there, everybody bigger there, right? Then I recursively sort this, and I recursively sort this, right? Everybody kind of get that? Now, the worst case running time is n squared. Why? Because you keep choosing the pivot to not split evenly. But the expected running time is n log n, right? Now you say, well, why don't I do merge sort? Well, this all happens in one array, and so it's fast, right? And you might not care that it's fast, but in the 70s and the 80s, computers were slow. And the fact that this algorithm was slightly faster than merge sort made a big difference to them, right? In fact, I think it's interesting what algorithm are the most computer operations doing? And in the 80s, they were sorting, right? And then in the 2000s, they were breaking cryptography, right? And what are they doing now? Machine learning, right? Right? So this mattered in the past, right? Everybody good? Right? This is saying, right? They're worst case coin flips, but not worst case inputs, right? So I can imagine saying, hey, in hashing, tell me what the worst case input is. The keys are the input. What's a worst case input? You'll say, there's not a worst case input. All the inputs have the same badness. Why is that? Because we don't know the coin flips yet, right? For any input, random coin flips, things go well, right? Does that make sense? I do think, I mean, that's core to random algorithms. And you're going to be doing random algorithms, and that's core to all of them. Why are we flipping coins? To hide stuff from the adversary, right? How are we doing? Oh, we got 7 minutes. Right? So breadth first search, right? It's using a queue. Says who's a depth, who's distance 1 from the S, who's distance 2, who's distance 3, right? You should know that, right? We're depth first search, right? You keep going until you get stuck, and then you backtrack, and you, right? You use a stack. You should know how to trace out depth first search in a graph, right? It's just, I think it's pretty core to computer science. And that's how far we got. Any questions about anything? Yeah, I meant to do it during my lunch, and I didn't. Why don't people bring up their phones? Right, so here, let me tell you what I want. I want when I come that there's people who come, right? And it's useful to you. So it needs to be late enough that you have time to study, and early enough that you can study for the exam after. And I've come up with a new requirement that it would be nice if the 1090 had it on the same day, right? So we could look to see when the 1090 exam is. You guys are in Easter, and they're a little bit before that, all right? So, and otherwise, my schedule is pretty empty. So how about we do this? I will look at the dates. How many days? Yeah. So and we'll make up a date, and I'll mail it to people. And if people don't like it, they can complain, and we'll have another hash. Okay? Yeah. Yeah. So next year, thank you. I take that as a compliment. Next year, I'm teaching. Have you done 2001 yet? Okay. I'm teaching that. And I always teach 31-1. There hasn't been a term, a year in 30 years that I haven't taught 31-1. Yeah. No, I got the best job ever. Yeah. And then you can ask which term it is, right? So here, times. All right. So here, 31-1 is in the winter. Oh, no, it's in the fall. And it's really weird. It's nighttime. Isn't that weird? It's Monday to Friday, 7 to 8:30. In fact, people in my community are upset because I have a party every Wednesday night, and it's going to have to move. Any other questions? Everybody good? All right. Well, do the course evaluations. Yeah. Yeah. Who's in 1090? When is it? All right. 28th, Thursday. And then when's Easter? Sorry, what, this? Oh, this is 17. Where did I get 28 from? 17. And then when's Easter? 20th. Oh, they're pretty close. Thursday, right? So anybody want to choose a date? Oh, I would say that was too tight here. What? This is on the 16th? We did it the 16th and the 17th? 18th? I don't know. How much sooner do you want it? How about the Monday? No, we got one no to Monday. Everybody got your calendars open? Somebody said no to Monday. You said Monday. Monday. Yeah, well, sometimes you got two things in a row, especially if we do it at 3. What time's your exam? We might be out. Your exam might be over already. Right. So then it'll save you coming in again. Right? Who wants to vote for Monday? Any objections to Monday? Any objections to Monday? You're objecting to Monday? Why? Yeah, but these guys do too. Yeah, but that's a lot of days. This is Monday to Thursday, dude.
Like, I think that works for like both of the people, so I think.
Yeah. What? Yeah, for sure. But that being said, how about this? If I get here and there are at least 10 people, I'll record it. If there are fewer than 10 people, I'll give them the answers and not record it. Yes. Zoom does it. I don't know. Some courses, does this one have a camera? I don't think we have a camera here, right? So really the problem is if we're doing slides, you'll get it. But if we're doing blackboards, you're going to be gone. Why don't we do same time, same room? 4 to 5:30. We're all used to that. What? On Monday, I won't have any plans in the evening. What? Now I do. Good. Everybody good? So learn the material. Do well. All right? Fill out the course reviews. I've said that before. Any other questions? Should we go home? It was a pleasure, everybody. Oh, thank you.